So modes like shift in the and not actually less. Bringing that on I see like that sequence. On it's great. No.
All right, so going to just kind of frame this session. We're gonna be slow in general. Obviously, loose acting basis is not such a big topic, but as we like to go through things, as we talk about other things, like when we review stuff, like I would like you guys to just be nice and slow, all right? I want us to like reset a bit. I know you guys have been like stressed, going through exam after exam, and so yeah, this session should be like a nice reset. And like my hope is also like for test taking techniques or studying, like if you guys are studying and it's doing well, like stick with it or whatever. But if you're open to like learning how to like study in a better way or take exams or take questions in a better way, have like ears to listen and instead of just like that, like listen carefully. All right, that's like what I'm trying to say. Okay. All right. So Lewis acid bases is not so bad. The only thing is that you have to also remember what we talked about earlier, right? We talked about Arrhenius acid and bases. We talked about Bronsted-Lary acid and bases, and now we're talking about Lewis acid and bases. And Lewis acid and bases are really interesting in that, just like Bronsted-Lary acid and bases, they kind of describe what a molecule is going to do at like in a reaction. So like Bronsted-Lary acid and bases, right? It will say, well, even both all the definitions kind of describe what they kind of do in a reaction, but I think Lewis acid and bases are a lot more general and can be applied to a lot of different things. So like we know, you guys need to know like the Arrhenius and Bronsted-Lary definitions, right? Arrhenius, um, does anyone know what the I don't know how to spell Arrhenius. Do you guys know what the definitions are for the Arrhenius definition? You guys remember? Uh, yeah, that's Bronsted-Lary. All right. Acids produce um, hydronium or H plus, produce um, H plus, and then bases produce hydroxide. All right, that's Arrhenius. Bronsted-Lary, Lowry, that's the proton donor, proton acceptor. So acids are proton donors and bases are proton acceptors. Acceptor? Tor? Okay, I don't know. But yeah, so one, like each is getting donated and then one's getting accepted. With Lewis acid and bases, it's a little different in that it's now talking about electrons. So there's electron pair acceptor and electron pair donor. And so when you want to think about this, a good example is like ammonia, right? Ammonia we know is a Bronsted-Lary base, right? If we draw out the Lewis structure, and yeah, generally speaking, like when you draw out the Lewis structure, that's when you use Lewis acid and bases, right? So you draw out the electron dot diagram, and let's say it's reacting with, I don't know, yeah, we talked about water, or let's say, should we do water? We could do water, yeah. All right, so ammonia is going to kind of join the hydrogen, right? The Bronsted-Lary acid base definition, right, says that this is going to accept the hydrogen from the water and then produce ammonium and hydroxide. Lewis acid base definition says that instead of it accepting the hydrogen, it's going to donate its electron pair. And so that's like when, I don't know if you guys have seen, like that's when I draw out these arrows like that. It's because the electrons are kind of attaching or like rounding that hydrogen. So the H
and the water as a whole is acting as a Lewis acid. So this is a Lewis acid in this case, and this is a Lewis base. And the key takeaway is that the one with the lone pair, I guess, is acting as a Lewis acid in this case. I don't like, I know it's going to be a little confusing because why doesn't the water act as a Lewis acid? It can act as a Lewis acid. However, in this specific reaction, like we've talked about ammonia reacting with water, we know what the product is going to be. We know that ammonia in this case is acting as a Lewis acid or a Lewis base. All right. Any questions? So like it's really important to just be aware of Lewis acids and bases because we did it in class where we went over like a couple molecules and we're asked like, is it a arrhenius acid? Is it a arrhenius base, brown cellulary base, brown cellulary acid, or Lewis acid, Lewis base, and you have to like be able to discern which one's which with that. But yeah, so let's do another example. Let's say, I mean, yeah, we could just do HCl and water. So HCl and water is another example, right? So now HCl is going to act as the Lewis acid in this case because it's not going to donate any electron pairs. However, water is going to donate electron pair and create a bond between that hydrogen. So like, yeah, basically it's going to produce like the Cl minus, right, with all the lone pairs right there. And then the H, it's going to produce the hydronium, which is like boom, 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 which is like that. But yeah, it's the same sort of thing, right? So Lewis acids and broncellary acids are kind of similar. But again, you have to just be able to know like distinguishing factors. This is dealing with electrons. The broncellary thing is dealing with the protons. There like could be examples where it's not literally like acids and bases. I'm trying to think of one. Well, we talked about one in class. With let's say like we have water and then boron trifluoride, right? We remember that boron doesn't have a full octet because of the way it is, I guess. And so oxygen can like create a bond with that boron. So typically, like the whole idea is, I guess like Lewis bases are what things that have like electron-rich things that can like donate its electron pair, and then Lewis acids are kind of electron poor for the most part. And like likewise, like you see HCl, even though HCl like Cl minus has like a lot of lone pairs in the states, it's kind of pulling the electron density from the hydrogen. And because it's pulling it, it makes this a lot more electron poor, which allows the electron pair to kind of join to hydrogen. You don't even know, like, I guess, like the logistics of it all. The question will be a little bit more straightforward, and you don't need to know the mechanism of how these reactions occur, but just be able to identify, okay, this is acting as a Lewis base, or this is acting as a Lewis acid. All right, that sounds good. Okay. So, yeah, this was like an example, or we just talked about boron trifluoride in that case. Yeah. And so this is kind of a different kind of topic. It's similar, I guess. So like, actually, no, it's pretty similar. So now we're talking about things that have like metals, right? So, you know, like hemoglobin, it has iron. There's a lot of different molecules in our body that have metallic ions, right? And those metallic ions also act as Lewis acids in this case. So if you note, right, for something like this, if like iron is reacting with this, let's say it's like iron 3 or something, I don't know, right? It's going to produce like these electrons, or these guys have like lone pairs, right? So like this ammonia is going to have like a lone pair. This ammonia is going to have a lone pair. They're all going to have lone pairs. And those lone pairs are going to attack that iron and produce, hello. Those lone pairs are going to basically attack this iron, which is a Lewis acid, and then produce these molecules that have called coordination complexes. And all it's doing is those lone pairs are basically acting like as bonds, right? How many electrons are in a bond? 2 electrons per bond, right? So it's basically creating a bond with the Lewis acid, and it's forming it. So, I guess like what's important to note is you should know, yeah, like how to count the number of ligands. All you have to do is just count the number of bonds from the Lewis acid. So in this case, there's 1, 2, 3, 4, 5. So there's 5 ligands. All right. There's going to be probably a question where they ask how many ligands are in this coordination complex. They'll give you a molecule like this, and you just have to count the bonds. It's just like sigma bonds, basically. 1, 2, 3, 4, 5. It's only going to be most likely all going to be sigma bonds, but yeah. All right, that's like the problem solving with that kind of question. Okay. And yeah, it is Lewis acid and bases. Again, like electron poor, and then this would be electron rich because of the lone pairs on the nitrogen. Okay. And so, yeah, he was going over an example in class where he was showing, like, say, like, silver reacting with ammonia, right? And you're not going to be expected to know the reaction off the bat unless he gives you the reaction or some information that allow you to write out that reaction. In this case, he said that 2 ammonias are going to react with a silver ion and produce like silver and then like that. And then it's going to be plus. I mean, one thing you can note is that the charge on the left is equal to the charge on the right. So that's like nice to tell. But again, right, this is acting as a Lewis acid. This is acting as a Lewis base, right? Ammonia has a lone pair. Silver does not have anything, basically. It's not that it doesn't have anything. It doesn't have anything in its outer octet. And so this is Kf, right? You can figure out the equilibrium constant for the rate of formation, all right? Additionally, you can also find Kd, right? How do you find Kd? Do you guys remember from module 4 when you had to like flip the equilibrium? And do you guys remember like how you flip the equilibrium? It's basically you just do like 1 over Kf is equal to Kd. I don't think he went over Kd, but I remember there was a question on it on my exam, I think, where he asked about Kd. And Kd is just dissociation, which is the reverse reaction, right? So Ag NH3 2 yields Ag plus 2 ammonia. Right? You can use Kf, K or Kd, but there might be a question where they give you Kd and you might be confused, like how do I get Kd, right? It's basically just yeah, 1 over Kf equals Kd. Or you could do Kd times Kf equals 1. Yeah. But again, it's like based off the equilibrium rules from module 4 with coupled equilibria, if you guys remember that. Okay. So yeah, we got a problem here. So let's try to do this. Give you guys some time to do this. And also just FYI, the -2 is the charge of the ion. Of the complex coordinate.
Make sure you. Yeah. And so if it was good money, maybe you just convert it and then put the fan. Yeah, or you just use AF and like just keep the same structure. Like, you know, maybe like let's say hypothetically, you only have a four-inch complex of info, they're asking you to find them. You can still use like set it up like this, yeah, even though it's technically associated. Oh, yeah, it's just not totally the point of it. You could do KP block too. Like, you just make it. Make it. Minus 2 times. And then 2 times. So like the charges is like the thing, like you don't even know how the reaction is occurring. The charge, right? You know, charge the left. Yeah. Yeah, like, I remember you telling me, how to not bring that up with, just like cross multiply, so like this denominator is going to 0. Like cross, right? So this small the one y now is in this and this and this. The trace numerator is gonna be like understand. So I think it's understand. Like, yeah. Right, and then that's like, is this number times this times this. Thank you. But the equation.
Yeah, I texted her. Asking her to go to the office.
It does, but it's always a little. It's like, oh, like. Yeah, I never really like put it in like a full fraction, I was possible, right? It's a little bit here, but it's a little bit of a.
Like you probably like.
Graph, yeah, like on the, which I just like fuck, so it's just like, yeah, out of the ocean. Yeah, so like, I'd say cross multiply, like, so it was not a, yeah.
Alright, I'm gonna get going and go over this. So one thing I made a mistake on is I put copper ions. That's big no-no, right? If you're giving copper ions, you need to track the molarity using the liters, right? I made a mistake here, so just an FYI. Whenever I see a question like this, on an exam, it might be easy to just be like, what am I looking for or whatever. I always like to underline. That's like just my thing. I don't really list out what I have because I think it's a little bit of a waste of time if you just underline the question. So like, let's see. They're telling you this reaction. So this is like a reaction. And they give you the KF, right? And then they're asking you to find how much complex ion. So this guy is formed if you have this and this. All right, it looks a little bit confusing, but when you do your exam, you'll like know what you're doing. So I highly recommend just like underlining things when you guys do your exam so you can figure out what you're doing. And so yeah, we see copper ions, right? And then chloride. Chloride is usually -1, so I'm just gonna put -1. It's forming CuCl4 -2. So if there is a -2 on the right, this is going to be very important when we get to electrochemistry, right? If there's a -2 on the right, we know that there's a -1. Well, first off, before we even do this, there's 4 chlorides there. Let's put 4 chlorides on the left. So there's 4 right here. And so now if there's a -2 charge on the right and there's a -4 charge on the left, what does the charge of copper have to be? +2, right? This is very important for when we go into electrochemistry. So it's also kind of a nice little trick to like figure out if you're writing the reaction right. And this is equilibrium, right? Even though the KF is super large, it's still an equilibrium, right? So we can do an ice chart. And we have 3.0 times 10 to the -4 copper ions, or not copper ions, like that should be the concentration. And then chloride is 4.12 times 10 to the -2, right? You do -x for copper. Make sure you guys remember the coefficients. So this is -4x for chloride, and then 0 plus x. X 4.12 times 10 to the -2 minus 4x, and then 3.0 times 10 to the -4 minus x. Okay. And then you want to make sure you know how to set it up, right? So it's going to be KF, or 1.0 times 10 to the 8 equals x over 3.0 times 10 to the -4 minus x times 4.12 times 10 to the -2 minus 4x to the 4th power. Make sure you guys remember that coefficient, all right? I think I got like a question wrong because I forgot the coefficient. So make sure you guys remember the coefficients when you guys do these kind of questions for module 6. All right?
And so after that, you just plug it into the calculator like we've been doing, and you get your answer. Let's see. So I got 2.99 times 10 to the negative 4. That right? That good? All right. So again, like this is just another example of ice charts, right? We've been doing this over and over and over again. All right. Even though it's a different like topic or module or whatever, right? It's all like branching off the same topic or idea of ice chart. All right. And so yeah, that's kind of all I had for I guess like not yesterday, but we're gonna do some review and stuff. Before we do that, I'm just gonna do a little bit of an overview of like what we've done, right? Module 4 covered. What did it cover? What do you guys think it covered? Equilibrium, right? So like equilibrium. What are some concepts about it? Oh yeah, coupled equilibrium, that's one thing, yeah. It also covered Q, right? Q versus K, right? What else did it cover? KP, yeah, it covered KP. Okay. Anything else? Hmm. Yeah. It also covered I guess like the state of equilibrium, like what happens at equilibrium. The concentrations are constant. The rate of the forward reaction equals the rate of the reverse. So I'm just put like two states at equilibrium. So about like five general things. I'm sure there's probably a little bit more. There might be something we're forgetting, but 5 things. Okay. All right, let's go to module 5. All right, what did module 5 cover? Okay, acid bases, right? That's the big idea. All right, tell me the topics. Yeah, strong acid pH, that's one, yeah. 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 pH equals POH plus pH or 14 equals POH plus pH. It also talked about Bronsted-Lary acid base definition, all the acid base definitions. Okay. What else did it cover? It covered KW. KW is part of this like reaction here, or it's part of this like expression, right? KW equals pKa plus, or yeah, KW is equal to 1.0, or KW, yeah, KW is equal to 1.0 times 10 to the negative 14 at 25 degrees Celsius. Okay, anything else? What else did it cover? Just off the top of your heads. It did cover salts, but you're kind of jumping the gun, right? It talked about weak acids and weak bases, right? Oh, it talked about salts and their pHs, and then also weak acids, weak bases. All right, what else did it talk about? Yeah, now we're getting to part 2, right? Polyprotic. Oh, go back. 1 second, sorry. Polyprotic acids. And then what else? What else? I'm just going through it. What else? Come on.
What is it, whenever we go from, like, we get the moles of it, like the sodium.
Yeah, that's part of the titration stuff, right? So neutralizations and titrations, right? So neutralization, titrations of strong acids, strong bases, weak acid, strong base, weak base, strong acid. Okay. or strong base, strong acid, right? The first thing in like whenever you say strong acid, strong base, right? It's implied that the strong acid is the thing that's in the Erlenmeyer flask. So that's the thing that is like in the Erlenmeyer flask, and the base is being like dipped onto it or like dropwise, right? So like yeah, that's like the thing that's in the Erlenmeyer flask. Okay. Anything else? Henderson Hasselbalch, good, right? Buffers. We talked about buffers. All right. Henderson Hasselhoff. I don't know how to spell Hasselhoff. Okay. Anything else? Okay. One thing I'd say is a very important concept. Stronger the acid, the weaker the conjugate base. The weaker the acid, the stronger the conjugate base. All right. So like, I'm gonna put that next to Brown-Still-Larry acid, or stronger acid leads to weak base or conjugate base. All right. All right. I think that's pretty good for this for module 5. I mean, I covered 2 modules, right? Module part 1, part 2, right? All right. Let's talk about module 6. What did module 6 cover? Yeah, solubility, KSP. All right. What else? Lewis acid and bases, right? We just talked about that. What else? It's not a trick question. What else? What else? Yeah. Yeah, coordination complexes. And then anything else? Anything else? Yeah, pretty much. It, I guess, like again, like ice tables, right? With all these equilibrium stuff, right? Yeah. So this is not a great list. This is an okay list. Like I didn't really write it well, I guess. Like, but this is like a good overview of like everything or about like generally everything that we like kind of covered. And it seems like it's a lot, but I feel like as you like go through it, you know, you kind of realize a lot of the concepts are being like are overlapping, right? We got like equilibrium is like literally every single thing. So if you know how to do like one equilibrium, you should be able to be familiar with how to do equilibrium for showing these concepts. But I'm just writing this all out because like I want you guys to feel like, oh yeah, we went over all of this and like I kind of remember how to do it, and it's not as overwhelming as I may think it's, right? I would say like one thing I would do is I would write out these kind of things and ask myself and be honest with myself, like, am I confident I can do this question on an exam? And if I'm not, I would check out that topic and make sure I was confident. And so like, let's say hypothetically you're not confident with buffers, right? That would be, I would put a star next to it. I'd be like, okay, let's do this, right? Let's make sure I'm good with that. Do a couple of questions, like ask myself, like, do I actually understand how to do these kind of questions? All right. Same thing with, let's say like polyprotic acids, right? If I'm not like strong with it, right? Do a bunch of questions with it. Make sure you understand how to do a question on the exam. And then, yeah, like that's kind of like what I would do, right? We've learned most of these things, and if you've been paying attention in class and doing the sample problems, I wouldn't expect you guys to study everything, but study the things you need to study for sure. It doesn't hurt to study everything, but you know, there's some things that you might need to pay more attention to. But it's a good general like overview. All right. And yeah, I'm here to help out with anything. Yeah.
Visualization contributions, is that only for ICF tables?
It yeah, basically it's usually for ICF. There could be a question where it's like, what's a like we talked about this question like last semester, but there could be a question like this semester where it's like, what's a like volume of acid needed to neutralize this base? Which is like you could do an ICF table for that, but it's just easier to kind of just do like the like a multiply it out, like figure out the moles of hydroxide moles of hydronium, make sure they're equal and whatnot. Like, yeah, they might say like HC, like, what's the volume needed to, what's the volume of NaOH needed to neutralize like 0.1 molar HCl or 15, let's say 15 ml of 0.1 ml, blah, 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 right? If NaOH has a concentration of 1 molar, right? Like that's like a question we talked about last chapter with like stoichiometry of it. And so for this, you could write the reaction out, and then you could do like 1 molar X is equal to 0.1 molar times 0. Or you could do 15 ml to get the ml amounts if you'd like. Or you could convert it to liters and get the liters, right? But yeah, you could figure out graphs like that. You want to make sure you also account for it being a 1-to-1 ratio. If it's not a 1-to-1 ratio, you have to account for that. But the whole thing with this is that the hydronium, the H plus concentration equals the hydroxide concentration, because when something is neutralized, that's what happens. All right. Okay. But anyways, so yeah, I just want to go over this like a little overview so that you guys can like make sure you or be honest with yourself, like where you need to focus on. Yeah, we're gonna do some questions. I'm gonna go over a question, and then after that, I'm gonna give you guys a little bit of a hard question. Okay? All right. So let me go to my worksheets. Let's see. Worksheet. Where is my worksheet? Worksheet 6. Mm-hmm. All right. I'm gonna go over an easy question, but I'm gonna give you guys a hard question because the way I'm gonna go over this question is like how like I go through an exam myself, or how I go through the question. Because I think half the battle is how you test it. And I know Professor Yusuf throws a lot of curveballs. He makes there be a lot of fluff. And so it's easy to get very lost in the question and lost in like without any strategy. Or like forget the strategies that you guys have learned as you guys go through this. But there's a lack of originality with a lot of these questions. If you guys saw like that list that we had, right? That's like all the kind of questions you could ask, right? So like if you are able to like answer those like questions, generally speaking, even if he throws in all that fluff or tries to ask it in a weird way, like it's still going to be the same question. All right. So let's try to do this question. All right. For this question, the way I would go about this, right? What is the pH of a solution containing that amount of acid and that amount of salt? All right. So obviously, when I see this, the first thing I'm going to see is what am I looking for, right? So I'll underline pH, right? So that's one question. And then another thing is I will underline what I have, right? So I have an acid and I have a salt, right, with its conjugate base. And immediately, when I see these three things, I jump straight to Henderson-Hasselbalch, right? Henderson-Hasselbalch deals with buffers, and this is clearly a buffer. They might not tell you it's a buffer, but you need to be able to identify that. And so then I go and I write out like pH is equal to pKa plus log of base over acid. And I put everything in, right? So there's a Ka value up here. So like you see there's no Ka value given in the question because it's all up there on the top. So if you look there, it's 3.5 times 10 to the negative 8. So we just plug it in. And you solve. So let's see. Yeah, negative log of 3.5 times 10 to the negative 8. And on the exam, you don't need to write everything out unless you want to be really confident. Sometimes like when I'm dealing with like a lot of math, I'd like to write it out just so that I plug it into the calculator better. So base over acid, 0.5 over 0.25. All right, so let's solve. Negative log of 3.5 times 10 to the negative 8 plus log of 0.5 over 0.25. All right. And so I got a pH of E of 7.76. All right. Boom, right? I explained this question in a minute. It would have taken me 30 seconds to do this kind of question on the exam, right? Um, of course, like when you're doing an exam, you want to make sure you understand like there's questions involved with like there could be questions where it deals with information that you're given earlier. So like that's one thing you have to be aware of. Okay? Okay. All right. I'm gonna give you guys a little bit of a harder question now. All right? Because I believe you guys can handle it. So let's try to do questions 15 and 16. I'll give you guys some time to do it and we'll solve for it. All right. So try this question. And whenever you guys don't know what an acid is or what it looks like or what its conjugate will look like, you can only default to HA and A minus. All right. So try to do that. And yeah, I emailed you guys. Oh, how did it go? Might do an extra SI session on Sunday evening as well. On Zoom. That one, I plan to just go over just practice exam and I guess go over my own like way of doing it, whatever, right? And then Monday we'll go over practicing that for the last 2 weeks. Yeah. So yeah.
Oh, for the, yeah, yeah, so. Like, what is it? So, I'm. Like that. Yeah. Maybe some Asian, either, I don't know. No, it isn't, it is the opposite, but it's not, like, this reaction effect of it, right? This is reacting with water. So this is, should be the. Yeah, so like, you could, right, oh yeah, I mean, these would be, like, it would be like two, three, H plus, pick up. Because anytime you see like, I'm using. Or anything that happens, or, yeah. And the names are just names, right, just what happens. Thank you. It's a hard question. A lot of people were confused when they took this question with minor. They're like, what is Sui Island? And why is like microcosms there, right? Like it's like something ends. Ends, right? It's confusing. Fine.
All right. How are you guys doing? Want a little bit more time? I'll give you guys like a couple of minutes. All right. So, gonna talk to you guys on doing the work. I know you guys spent a lot of time trying to like probably figure out how to do it right. Because it's a little bit of a hard question, right? He gives you a lot of useless information in the beginning, and then he gives you one part of the lesson and the second part. Lesson. But yeah, nothing that he can't handle. So I'm just gonna go back to like our little concepts that we talked about, right? We have all these different concepts. I want you guys to tell me what concepts did we like go over in this question? Like from the list that we have. What concepts will question? That we shout it out. Yeah, salts and pH, right? We talked about salts and pH, right? So that's one thing. Oh, wait. Yeah, so that's one topic we talked about. That's literally all of question 15. What other thing did we talk about in this question? It's a little bit more obscure, but it's still something we've talked about before. Anyone know? What? Like, I mean, yeah, it's an acid base, right? But like, what kind of thing? It's a little bit hard, but we did a little titration, right? We added some acid to a base. Specifically, we did a weak base, strong acid titration, right? Even though you're still even though it's not traditional titration with the burette, right? You're still adding like an acid to the base and you have to figure out what's going on, right? So like that's the second part of the question. And so when you do these kind of questions, or when I do these kind of questions, instead of like trying to figure out or spending a lot of time trying to figure out what is going on, I think it's really important to figure out like, or instead of trying to figure out how to do things, I think the first thing you should try to figure out is what are we being asked, right? So in this first question, it's a salt, right? With a conjugate base of a weak acid, right? And so we see that N3 is there. The difference between the conjugates is just one proton, one of each plus, right? So we see that this is the conjugate base of hydrozoic acid. And we're asked to find the pH, right? It's the same thing as if we did sodium acetate, or the same thing if we did another like conjugate base with a like an ion, right? Salt or whatever, right? So yeah, that's like 15. 16 is what happens when we add these to that, right? So if there's a strong acid being reacted, what's the strong acid going to react with? Like if the strong acid's in a reaction, when is the reaction with? Right? What's the name of the unit? Right? So strong acid is going to react with its base, right? Right. So we have in the solution conjugate base or base, right? So we have a strong acid that's going to react with its base. All right, does that make sense? Okay, and then that will produce whatever reaction of that. Okay, so like I always like to just identify like what concept is or whatever I'm like learning or whatever I like have learned, and then by doing that I can kind of like start applying that instead of like just jumping out of the like in the dark with this or shooting in the dark. That's the term.
Okay, so let's see this, right? So we know that this is salt. So this salt, it produces sodium plus and N3 minus. Okay? Like that's something we've talked about before, right? This N3 minus is going to be a base, right, in solution. It's a conjugate base of a weak acid. And so if it's a base in solution, it's going to react with the water, produce. See ya. No problem. It's going to produce, right, a base in water or a base in solution. It's going to produce hydroxide and the conjugate acid. So HN3 like that. Okay? And so what's happening here is we can do an ice table and we can figure out the hydroxide concentration. And by doing that, we're able to figure out the pH. So 0.1, blah, 0 plus x minus x, 0.10 minus x, right? We've done these kind of questions before. Anytime we've done a weak acid or a weak base in solution, boom, like you just do an ice chart and you do x squared over whatever equals the k, like k, right? In this case, we're going to use kb because this is a base, right? If you're able to identify that this is a conjugate base, we need to use the kb, all right? And so now it's going to be kb, right? How do we figure out kb? It's kw equals ka times kv, right? So let's do that first. 1.0 times 10 to the negative 14 divided by 2.5. 10 to the negative 5. So I'm putting in the calculator. 1.0 times 10 to the negative 14 over 2.5 times 10 to the negative 5, which is the k that's given. And that will give me 4 times 10 to the negative 10. All right, that's kb. And that will equal x squared over 0.100 minus x. All right, and then you solve the way we've been doing, right? Y1 is equal to, I cross multiply, so like in the calculator, I'm going to put this value times 0.1 minus x equals, and then x squared, right? So yeah, I'll put this one equaling like y1, and then y2 is equal to x squared, right? So let's do this. So x squared, and then this is going to be cleared 4 times 10 to the negative 10, 0.1 minus x. Okay, and then you do second calc, and then you intersect and you find the x intercept. So enter, 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 and I got a value. Oh, that's not right. Okay. Why am I getting anything? Are you getting a negative value? You guys set it up like this, right? Did I put something wrong with the calculation? Hmm? What? Yeah. I don't know. I got 6.32 times 10 to the negative 6 as my x value. You just want to keep doing it until you get um, a value, right? And so after you do this, that's the value for hydroxide. If you press X on your calculator, you get the you get the X intercept on the calculator. Yeah. And then you could do negative log of X, which is the POH. And then 14 minus the negative log of X is the 8.00. So 14 minus the negative log of X is equal to 8.80. All right. Is there any questions you guys have? Yeah. 0.01. Well, you're right. Good, good, good. Right, good. That's a very good mistake that I made. This is a very common mistake, right? You want to make sure you put the right number, right? That's very important. So that's like a big thing. You want to make sure you check your work. Yeah, I'm not gonna play it off like knew what I was doing, right? Let's see. So that changes things a little bit. So I got the wrong Vex value. So, boom, boom, boom. All right, now I got a better X value. X value is 1.999 blah, blah, blah times 10 to the negative 6. It's because I put something wrong in the calculator. This is supposed to be 0.0, right? 0.0. That's my bad. All right, so you want to make sure you're just putting in the right numbers, right? Sometimes you can get a little bit flustered, right? That's why it's important to underline things too, okay? I didn't underline things when I did this, okay? So now, if I do 14 minus the negative log of x, I'm gonna get 8.30, okay? All right. All right. So we just did a lot of stuff, right? But I was trying to, I guess, explain this all to you, right? It looks like it's a lot of work, but realistically, these kind of questions, like if you guys are able to identify what you have immediately and like know how to, because you identified the concept that's being asked, now you're able to solve this concept. this question really shouldn't take that long, right? All we did is like you don't even need to write out this step if you understand that stuff, like with the salt dissolving. All we did is the ice chart, and then we did x squared over whatever, and then that's the equilibrium. And then after that, we did the normal IGC, guys. Where we equaled it to KB, and then we solved for x, and then we got the value. And then from there, you can take the x value on your calculator, you put x, after you find the intersect, you get the number for x. And you can do 14 minus the negative log of that to get the pH. All right. So this question, if you guys are really good or you guys practice a lot with this, should take 3 or 4 minutes. All right. And why I'm like stressing to, I guess, go a little bit faster. You might like think you're going to make more mistakes, but it might be advantageous to be. It's better to go fast, be fast and accurate, than be like slow and not know what you're doing and then making a mistake. That's why I'm like suggesting to practice all those like concepts or whatever concepts you think are weak concepts for you. Okay, so yeah, we just did an ice chart and then we plugged it into the equilibrium and then we found x. Basically, that's all we did, right? It just looks like it's a lot of work because I made a little bit of a boo-boo and I was explaining things, right? All right, for 16 now, we have nitric acid, right? So a lot of people might be confused because it's like, oh, there's a nitrogen, right? It's a little bit confusing, but don't think of it like that, right? This nitric acid is reacting with the base that's in the solution, and it's going into completion and producing the conjugate acid and its conjugate base, like that. All right? That's the reaction that's occurring. All right? Again, it's like Bronsted-Lowry acid-base definition, right? That's always like the underlying theme, right? We see that this is donating a proton, this is accepting a proton, and likewise, right? You could also say that this is like acting as a loose base in this case. That minus charge implies that there's an electron pair. That electron pair is doing the hydrogen and producing whatever, right? And so, yeah, I'm just trying to ask concepts, right? So now what we can do is we do ICF, right? We see that there's a strong acid, weak base that's reacting with one another. We do ICF. And so now we take the volumes, right, and find the moles, right? So 0.755 times 0.01. So this is the moles for the azide compound. For nitric acid, it's 0.035 times 1.1. It's 0.0035 here. And this is 0, right? So we see here that there's more azide than acid, right? So we can subtract this from this. And you get 0.00405. And this is going to be 0.0035. So this is going to be minus, minus, this is going to be plus. And this doesn't matter. The nitrate doesn't matter. Okay? So now we have moles of N3, moles of HN3. And we're able to find the molarity of those two things. Well, before I do that, right, we got weak acid, it's conjugate base in a solution. And we have the K value, right, from the previous part of the question. What can we do? All right, I want you to verbally say, what can we do? Henderson, yeah. We have acid, weak acid, strong or conjugate base, and then we have the Ka from the top. So we can do Henderson-Hasselhoff to find the pH. So let's do that. So first we have to figure out the volume. So 755 plus 35 is 790 or 0.79. So 0.79 liters. So that's to find the molarity. And so this one is 0.00512, blah, blah, blah. And then the other one is 0.0035 divided by 0.79. or 0.0044, blah, blah, blah. All right. Make sure you remember pH is equal to pKa plus log of base over acid. All right. So the base in this case is going to be the azide. So that's 0.00512, blah, blah, blah. And then this one is 0.0044 dot, dot, dot. And then the Ka value is the one at the top here. So that's P is equal to, or pKa, so negative log of 2.5 times 10 to the negative 5. Negative 5. Okay, just trying to make it look a little nicer. All right, and then that's how you figure out pH. So negative log of 2.5 times 10 to the negative 5 plus log of this over this. Okay, and I got a pH of about 4.66 or 4.67. All right, does that make sense? Do you guys get that? Okay. We went through that a lot better, but yeah. So my big takeaway with these two questions, that the reason why I show this is I remember last 2 years ago when I took this exam and everyone was really confused about this question because it was like we never seen sodium azide before. We had never seen it react with something that also has like nitric acid. Like everyone was confused because at the end like it was just confusing and it was like the first time seeing it, testing value and stuff. Even though you guys have testing value, guys, like, or if you do have testing value or whatever, right? We've done these kind of questions. That's like the point that I'm trying to drill on, right? These kind of questions that we see here are questions that have just been slightly altered, slightly changed, right? Instead of it being like a sodium acetate, it's now a sodium azide, right? Instead of it because it's azide, it's like it's still a weak, I guess a conjugate base of a weak acid, right? So yeah, like my big takeaway with this is that like you guys already have like worked hard, you guys have done all of these kind of concepts. And so with that, like when you guys do these questions, don't try to spend so much time figuring it out as opposed to like, or figuring out how to approach the question, try to figure out what the concept is being asked, right? What am I being asked here and like what is given in this question? Like we see here in 16, right? After we do the ICF, we see that we have the weak acid conjugate base and we have the K, right? Henderson acetone, right? If you're able to like identify that, it saves you so much time. Same thing with the top one, right? If we see we have a salt with a conjugate base, boom, we do an ice chart. Saves you so much time with like trying to figure out what to do because you already know what to do. The only error is like if you make a mistake like I did, right? But even then, you save time by like knowing, I guess, what to do after knowing the concept. All right. So that's my like big takeaway. So when you guys are studying, because I know you guys are gonna study for this soon, make sure you guys go through these modules, see what works or what is like what you need more help in, and focus on those things. And let me know if you guys have any questions, okay? Because I know it's a lot. I know it can be a lot. So I'm here for you guys. You guys, your tuition's like paying for me. Low key. Low key. But yeah, like please, I'm here for you guys. I'm doing my best and you guys are doing your best. You guys got this. I believe in you. All right. But yeah, I hope you guys have a good day. Let me know if you guys have questions. Please email me if you guys like have like individual questions or anything. Or if you guys want, like I can like meet up with you and like we could like go over things too. So yeah. All right. See you guys. Bye.
But why do you neglect the NO3?
Oh, it's because it's like a conjugate base of a strong acid, right? So the stronger the acid, the weaker the conjugate base. So if you're dealing with like a literal strong acid, nitrate doesn't matter. That's why like sodium chloride, right? Like a solution of sodium chloride, the pH is 7. Chloride is a conjugate base of HCl, right? But like because it's so weak,
right? It doesn't affect the fees at all. Yeah. Oh, yeah, what I was saying is, all it's about is basically like, you have like a metal cation that's reacting with some sort of thing, right? And the whole idea is like, this is acting those leaves acid, it's acting in these states. And like, those there's, the ammonia, I would basically attack the electron or metal and trade from. It's kind of alive. So like something like this, compound here, like, that's with a lot of ends, right? That's a lot of them, yeah, iron will, oh, iron will, that's the electrons from the ocean, right? And then it happens. So like, this thing called ligand, right? It's saying like, let's say ions and molecules surrounded by it. All you have to do is, we might give you a question like on exam, where that's gonna be like how many ligands are there, right? And all you do is come along, yeah, I'll show the picture. Yeah. You have to count all the bonds from iron. Like, this is like a little, but you have to just make sure you're aware of what's going on.
And you said it was a double bond, it's still with kind of thing.
Yeah.
There could be like extra life in these that are charged, maybe it's the reason how. With those kind of ligands,
No, it's just anything that's like actually bonding. Yeah. Yeah, it's chilly, okay, like module 6 is like, it's like a little like. Oh, yeah, that's why it's saying on. And I was kind of like, yeah,
See you guys.
thank you.